afternoon, everyone. So I'm William Easdown from RAL Space, so nice to see us mentioned in the previous talk as well. So I'm on my year in industry at RAL Space at the moment as part of my degree. And this is William Brzozowski, who's on the graduate scheme at the UK Astronomy Technology Centre up in Edinburgh. So today we're going to be presenting about the CubeSat camera that we've been working on for the past few months. So these are the sorts of things we're going to be going through in our presentation. On the right hand side there you can see a rendering of the camera itself. But we'll talk a little bit about what the camera is, what it's designed to do, how we came up with the design and the requirements, the sorts of applications that we see this being used for, and then we'll outline the individual systems. So first of all the detector, then we'll go a bit onto the optics, and then how everything goes together with the optomechanics. And we'll also talk a little bit as well about the challenges we've had regarding signal to noise ratio. So first of all, CCAM, it's a collaboration between the UK Astronomy Technology Centre and RAL Space under the umbrella of STFC, the Science and Technology Facilities Council, which has now become part of the UK Research and Innovation Organisation. So CCAM is designed as a modular system, and it's also meant to be low cost. So we're hoping that customers will be able to buy CCAM off the shelf and easily integrate it into their own CubeSats. So it's comprised of an optics module, which you can see there in the pink and green, and a detector module, which is mostly the sort of the white piece at the back, but the grey piece between the two is the interface plate. So it's 1.5U long in total, so we're targeting this at 3U CubeSats, although there's no reason why it couldn't be used on bigger ones as well. And in terms of resolution, we're aiming for a 5 metre, have designed it for a 5 metre ground sampling distance at 400 kilometres above the Earth, which is about 2.6 arc seconds. We're aiming for orbital ranges of between 400 and 700 kilometres, so the 5 metre GSD is for 400. We're using a CMOS sensor with a resolution of 2000 by 2000 pixels, and the camera overall has a field of view of about 2 degrees. And in terms of lifetime, given the radiation environment and other factors, we're aiming for 1 to 2 years of use from this camera. So, as I've previously mentioned, we're aiming for this to be an off-the-shelf system, and to do that we're also using off-the-shelf components, and this helps drive the cost down as well. As I also mentioned, it's compatible with a 3U CubeSat bus, so you can see a render there of how we envisage it fitting into a typical bus. We've got an RGB Bayer pattern on the sensor, and on the CMOS sensor, and an FPU on board in our electronics package to control the module and to interface with the rest of the CubeSat electronics. We've got a single aperture on the front of our camera, and then the optical telescope, or OT system, which is along that longer axis of the 3U CubeSat. And then in terms of image quality, we're aiming for level 2 on the NERS scale. So in terms of applications for our system, we're mostly aiming at Earth observation. So we've put an image on the right hand side there of this sort of image you could expect to see from this camera. But as this is an interplanetary conference, we're also aiming it at interplanetary applications. So, for instance, geological activity, and essentially we're trying to make the camera as adaptable as possible, so customers can take our camera and use it for hopefully whatever they like, as long as they sort of keep up with our requirements. So, finally for me, I'll talk a little bit about the detector module. So, on the right there you can see a model of the detector module within its casing. So, as I've mentioned, it's 2000 by 2000 pixels roughly, and an FPGA on the single PCB, which is used for control. There's also some memory in there, which is used for buffering between the FPGA and the onboard computer. This is so that if the onboard computer hangs up at all or needs to do other things, we've got a small delay that we can use so that we don't lose data. In terms of power supplies for the camera, it runs off of the 3.3 volts and 6 volt lines that are typically found on CubeSats. So the 6 volt one is that you'd have straight from the solar panels. And then there are several other voltages that we use within the PCB, but they're all generated internally. So we use low noise linear regulators to generate all the other voltages that we need. So our power requirements in terms of lines and their types are fairly simple. We're not going to be drawing any more than 2 amps from a single line, and we're trying to keep the overall power consumption low, and we're thinking at the moment about 6 watts is what it's going to end up being as a maximum. In terms of frame rate, it can take a picture every second and a half, so 2/3 of a frame per second, you could say. And we're using quite short 500 microsecond exposures to make sure we minimise the blur, because when you're orbiting 400 kilometres, you've got to make sure that you're doing nice and quick exposures because of the high orbital speed. In terms of operations, we've also included a selection of power modes, so that means you can easily enable and disable components to save power or have maximum functionality. And in terms of thermal control, to reduce power consumption and complexity and size of the module, we're using passive thermal control.
So now look at the optics module. First thing to notice is that CCAM is a reflective design, and that was determined by the fact that we required 5 meter GSD and a typical LEO orbital height of 400 kilometers. That determined a necessary focal length of about 520 millimeters. Doing that with a refractive design, considering the volume constraints, wasn't feasible, so we needed a reflective design in order to fold the light back and forth within that small volume. It's actually a Ritchie creating design system, and that means that the primary and the secondary mirrors are hyperbolic mirrors, and that just further helps reduce off-axis aberrations. You can see we've also included a field corrector just in front of the primary mirror. That's there to reduce chromatic aberrations and to flatten the field. We also have 2 baffling systems, cone-shaped and tube-shaped. They're there because we're designing for Earth observation, and there's a lot of very bright straight light in the Earth. So we've had to completely block all direct straight light. Our central lens, the central tube path will also act as a mount and field corrector. Just behind the primary mirror, we have an infrared filter, which is one of our low-cost stock parts we're using. That's to block out light rays above 700 nanometers and allow accurate color imaging. It also gives the option that if the customer desires, we could remove that filter and perhaps use a monochrome detector for near-infrared imaging. So the performance of the optics module is actually very good. It gives a diffraction-limited RMS spot size across the full wavelength range, where typical wavelength range invisible and near infrared. In fact, the RMS spot sizes are smaller than the pixel sizes of 5.5 microns, and that's not necessarily relevant once you're beyond the diffraction limit, but it gives us a good margin that once you consider alignment and manufacturing tolerances, it still means that CCAM is going to perform well. The graph on the right-hand side is showing the RMS wavefront error in waves across the full field of view. That too shows diffraction-limited performance, and the blue curve there is particularly high because we're using radiation-hardened glass for field corrector, so you get quite low transmittance at lower wavelengths. You can see it's still performing very well. One other point I should mention is this is obviously the nominal system you're looking at. It's a theoretical model, but we've taken extra care to design in very careful alignment technique and control of the relevant degrees of freedom of the mirrors and the lens, such that we will be able to still achieve a very good performance considering manufacturing tolerances and alignment tolerances. So now a look at the optomechanics of CCAM. The optics module and the detector module combine together via a 3-point kinematic mount to preserve the optical alignment. We've also factored in mounting mechanisms to mount to various CubeSat structures, because that's out of our hands. It's the customer's choice what CubeSat chassis they want to use, and we want to make it truly modular so that it can fit to a wide range. We've also working on designing passive thermal compensation features, because it's particularly sensitive to the separation between M1 and M2. So we need to keep that distance pretty much set across the typical temperature ranges you might expect. We're also designing radial thermal compensation features, so with the compression and expansion of the mirrors, the chassis doesn't squish on the glass and crack it or anything. And finally, we've also considered vibration dampers in the design for the mirror cells, and that's to mitigate against various launch vibration modes. So now just a discussion about one of the main challenges we're facing in CCAM, which is signal-to-noise ratio. There are many limitations to the signal-to-noise ratio of small CubeSats. So main one being one of the main ones being the volume constraints, which limits your aperture size. So you're limited to how much signal you can actually receive. The well capacity of the sensor we're using limits the dynamic range, and given the orbital speeds, we're limited to about 500 microsecond exposure, which again limits the amount of signal you're receiving. When you get down to such short exposure times, shock and readout noise becomes significant, and as you increase in temperature as well, darker becomes more significant. So these are just some of the signal-to-noise ratio challenges. But despite this, we're still expecting to achieve an NII-RS level 2, represented in the images you've shown. So you might expect just large buildings, boats, fields, that sort of size is what we're looking at. So some of the possible solutions we've considered as well are image stacking, longer exposure times if it's possible to integrate CCAM into a CubeSat structure that was changing its attitude as it orbits, and continually looking at the same point. Or another one is deployable apertures, so that you have a larger aperture, you're collecting more signal, and that helps your signal-to-noise ratio. And the images shown here are just another project we're working on in the UK ATC. One of these it's a deployable mirror design, which fits inside 2U volume, and it's a 300mm aperture. So, quick summary. CCAM is a modular, low-cost imager for CubeSat platforms, going into space and launch environments. It's a 3U large CubeSat using a CMOS sensor, and the FPGA as well. Performance is very good, even considering alignment and manufacturing tolerances. It's quite high resolution for such a small imaging system, and we expect to achieve the NII-RS as level 2. Thank you very much for your time. Any questions?
Yeah, hi. Thank you for the information. It's very informative. I had a quick question about the trade-off you were discussing about with the image blur and exposure time. So I know of a few digital image processing tools which can actively mitigate blur. So why are you avoiding blur by minimizing your exposure time when it can actually be, you can have a better exposure time than what you are actually using?
So the main reason for that, we're trying to keep the electronics nice and simple, and one aspect of that is the FPGA we're using is a rad hard one, and it doesn't have a huge amount of capacity within the FPGA for the code. So the code we're trying to keep simple. Sort of image processing would be the sort of thing you'd have to pass off to the CubeSat onboard computer, but we don't want to push any big requirements like that onto the customer because we want to have this as modular as possible. So we're limiting what the customer has to accommodate, and also keeping it simple within our own system as well.
Hi, so I have a question about the lifetime you stated. You said 1-2 years. Obviously, for interplanetary missions, that's not quite enough. I'm probably biased because I think of Mars, but it would take a year just to get there. So, do you have any plan to increase lifetime, or what are the factors that are limiting your lifetime right now?
The main factor is radiation at the moment. So we're using the off-the-shelf sensor, the CMOS sensor. The radiation effects on there are the main driver of the lifetime. We will be considering adding extra shielding or other measures to combat those radiation effects if customers want to use this for interplanetary applications. But for this initial version, as we're targeting it at observation, the sort of 1 to 2 years is what we've got at the moment. But we're happy to talk to any customers about their particular requirements.
If you look at the sky, have you got an assessment of the magnitude limit without considering the exposure time, that is a bit short, but you could make it longer? So, talking about noise and so on. So, what is the magnitude limit for a star?
I don't think that's something we've especially considered, to be honest.
Do you mean astronomical purposes?
Yes.
Yeah, we haven't looked into that just yet. Primarily designing the observation and planetary observation of them, but certainly it's...
Do you think it will be difficult to look at medium bright stars like magnitude 7 or 8?
It should be doable. The optics and sensor can all transfer over. So yeah, we'll certainly look into that.
Any further questions?
Maybe I missed it, but you didn't speak about price. What will be the price of this kind of camera?
Okay, so we're hesitant to put an actual number on it at the moment, but we've certainly been talking to various organisations who've launched CubeSats, and we're going to make sure that it's towards the lower end of the price range and compatible with the sort of figures that customers would expect to pay. We're not going to make it anything ridiculous.
Okay. So you got pretty nice mirrors into the telescopes. Do you do them in-house or do you put them?
The mirrors.
The mirrors, yeah.
So the mirrors, no, they're not made in-house. We'll be procuring them elsewhere. But where at the ATC, there's a long heritage of building custom mirrors. So we've got good links with mirror manufacturers, so it shouldn't be a problem.
Any further questions?
Maybe I missed what was the resolution?
Yeah, so the typical low Earth orbit of 400 kilometers, we're aiming for 5 meter ground sampling distance. Translates to 2.8 arc seconds per 1 pixel.
So it's like that, something around that.
Any last questions?